Good morning, everyone. I'm happy to be here and present our paper, Defeating Slow and Low Threat via Diffusion Model-Based Generative Inference. This work is a collaboration between Ewha Women's University. Here is the outline of my presentation. Modern production servers are positioned behind content delivery network to improve performance and enhance security. In this regard, CDNs served as the primary shield against volumetric and application layer attack. Because they sit as the edge server, they can filter and inspect traffic before they ever reaches the protected servers. At the same time, CDN is designed for extremely high throughput and ultra-low latency, serving massive number of users simultaneously. But to handle that scale for defense, CDN must keep a short flow measurement window, often an order of few seconds, due to the memory constraint. This creates a gap where an attacker can exploit this short observation window to launch slow and low rate attacks that stays under the radar and evade correct detection system that lack behavioral flow monitoring. To see why it is challenging to detect them, we have studied over 80 types of attack flows, and we group them into two categories: slow and low and burst and volumetric attack. As shown on the left figure, burst and volumetric attacks are highly bursty with large traffic volume and high activity throughout their lifetime. We observe that they typically last less than 5 seconds with over 50% activity. This makes them so easy to capture within a short observation window. However, slow and low attacks generate much lower traffic volume and activity, and they spread their behavior over a much longer period, like 40 seconds or more. Because of this, they can easily evade detection system with short observation window. On the right, we show 5 categories of slow and low attacks: data exfiltration, C2 communication, DDoS, botnet activity, and surveillance. While they share similar pattern in terms of activity and duration, they differ in flow level statistics. This infers that we need a scalable packet-level flow behavior monitoring with a unified multi-class recognition. To have such a system, there are a couple of challenges to address. First, lacking scalable flow behavior monitoring. So the idea is that many existing flow monitoring and detection systems assume unbounded memory. They're basically storing per flow features at packet-level granularity using memory-intensive hash table, effectively treating memory as unlimited. These extracted features are then fed to various models such as LSTM, VAEs, and others. However, this assumption is impractical for line rate deployment, especially as edge traffic has increased from around 10,000 to 50,000 flows per second over the last decade. Alternative approaches choose for selective flow monitoring, where they reduce the overhead by only tracking a subset of traffic, which of course reduces visibility and creates a loophole in the system. Second, evading coarse behavior-based detection. State-of-the-art approaches for flow measurement mainly rely on flow-level aggregated features, such as packet size and inter-packet delay distribution. However, this design overlooks packet-level temporal dependencies and rich metadata within the flow. While the design helps with resource constraint, the highly aggregated features allows an attacker to forge attack flows to mimic benign patterns, and at the same time hiding their malicious behavior. As shown in the left figure, attack and benign flows are identical when viewed through this flow-level distribution. However, once we see them through the temporal dimension, they exhibit completely different behavior. Third, partial view of slow and low attack. Training machine learning model offline on completed flow data and then deploying it during the online detection is a common practice in current approaches. However, the data set on completed data is almost unavailable during online detection, especially in the dynamic network environment. Most of the state-of-the-art systems rely on hard timeout or threshold-based heuristic, effectively working with the partial observation of flow, which causes high false positive or low detection rate during early stage of a flow. This partial observation is essentially more challenging for slow and low attack. Simply waiting for completion is infeasible due to the sparse and long duration of activity. As a solution, we propose SketchVision, which is designed for deployment at edge server of CDN to protect production servers from slow and low threats. At the edge server, SketchVision operates through an eBPF-based monitoring model running within the kernel. and it is equipped with GPU for AI-assisted tasks. Within the kernel, the system consists of several key eBPF components. Our sketch data structure, which we call it sketch universe, where the flow behavior monitoring takes place. We have flow table, which maintains metadata for each flow, including flow ID, initial timestamp, and flow size. And we have the ACL table to enforce security policy for blocking malicious flows. First, the sketch universe encodes each flow into a compact image representation by transforming packet-level temporal relationship into a geometric structure. The idea is that we want to preserve the flow's behavior. This region is then mapped to user space for data retrieval. Next, a detection trigger is built directly within the sketch encoding process using a small threshold. When this threshold is exceeded, it activates detection and notifies the user space XDP agent by passing the ID of candidate flows. The XDP agent then retrieves the corresponding data from the sketch universe and triggers a series of AI pipelines. Once the XDP agent retrieves the data from the sketch universe, it passes through a denoiser to denoise the sketch and feed it to the forecaster to derive the mature state of the flow from partial observation. And finally, we classify the flow. Based on the classification result, we use the ACL to take proactive action for early mitigation of slow and threats. Now let's dive deep into each of these components. First, we extend the conventional per flow counting sketch into a vision-based representation of per flow behavior, a process we refer to as flow painting. For each incoming packet belonging to a flow F, we first apply a pair of independent hash functions to map the packet to a base point within a 2D sketch universe. Subsequent packets are then encoded relative to this base point by transforming their temporal pattern into polar coordinate using angle theta and radius r. Here, r captures the average packet arrival time, and theta represents the timing of individual packet. Once we derive the location of each packet, we encode packet metadata into a 24-bit pixel value represented by RGB. This process repeats for every incoming packet, we progressively painting a visual representation of the flow's behavior over time. This process applies to all flows in the network, but where all flows paint their flow behavior into a shared memory space called sketch universe, which of course collision and flow interference is inevitable. During detection, we locate the region associated with the targeted flow, we crop the corresponding portion in the sketch, and we pass it to the ML for analysis. Now let's go over machine learning pipeline. Once the flows are encoded into the sketch universe, the cropped images are noisy due to the random memory sharing between them. And these images are not directly interpretable by the classifier. Now the key challenge is how do we drive the clean image from the noisy observation? Our intuition is that this noise is primarily driven by supervised flows, which eventually converge toward Gaussian distribution in line with central limit theorem. Based on this, we leverage diffusion models using their capability to reconstruct signal from Gaussian cropped data. However, standard diffusion models are designed to reverse the input back to the anchor point. Basically, their training and reversing is based on a single image. Basically, during the forward process, they take an image and progressively add diffusion noise to it. And during the reverse process, they learn to iteratively reconstruct the same anchor image. But what we need here is a bit different. We need to get a clean image directly from the sketch noise, the sketch noise variation. So I skip the details here, but our key novelty is a dual guided diffusion strategy. We keep the same forwarding process as it is, but during the reverse diffusion, we train the model to recover clean image from Gaussian cropped input. We do this by jointly learning both flow dynamics and flow semantics for multi-recognition denoising. Using this approach, we teach the model to reconstruct clean image from a noisy sketch across all stages of its progression. Next, once we're having the clean image of the flow, now the question is how we derive the mature state of the flow from the partial observation. before passing it to the classifier. So we adopt a similar strategy in Sketch using for our training of the denoiser. We iteratively add Gaussian noise to the partial observed flow. And at each step, we train the model to give us the mature state of the flow used by adjusting the loss function. This way, we teach the model to generate mature state of the flow from partial observation, again, across all the flows progression. As a summary, once we obtain the cropped image from the sketch universe, we first denoise it, then we forecast the mature state of the flow, and then we pass it to the classifier for a multi-class recognition. Now, I'll move to the experimental result. We have developed a prototype of SketchVision with 3 main components. We have a vision-based behavioral sketching model implemented in eBPF kernel. We have a user space program called XDP agent, and it bridges the in-kernel sketching with the user space AI pipeline. Our diffusion model is based on conditional unit using OpenAI code base, and we are using a multi-class CNN. Our testbed is an edge server with 64 CPU cores, 1 terabyte DRAM, and NVIDIA 800, which we use for our training and inference. For training the diffusion model, we use 19 type of slow and load attack plus benign traffic. So we have total 20 types of flows. We train both the denoiser and forecaster across the full progression of each flow type. In the experiments I'm going to talk about, we use pair of clean, noisy image and the corresponding mature flow states. Now I'll present the early detection results by comparing SketchVision with state-of-the-art flow level and packet level ML-based attack detection system. The task here is to classify a flow using only partial observation, using up to 150 packets. Here we allocate 12 megabytes of memory for bounded memory approaches, namely SketchVision and SketchFeature, and we relax other unbounded memory schemes. As shown, both packet level and flow level approach struggle to detect malicious flow from partial observation due to the absence of behavioral monitoring and forecasting mechanism. In contrast, SketchVision outperforms all approach through per packet flow behavior monitoring, where combined with diffusion forecasting, achieve 93% F1 score with only 20% of flow observation. Now I present a several visual example across 5 categories of slow and low attacks. These samples are cropped from the sketch universe, and they are difficult for human eyes to distinguish the noise and the flow's behavior. We denoise them by passing through our diffusion denoiser and then to the forecaster. And as you can see, the predicted results are very close to the ground truth. Now I focus on sketch denoising performance. We first evaluate pure behavioral monitoring with no sketch noise in place. As shown, it achieves near perfect detection on clean images, confirming the effectiveness of the temporal over feature representation. Then we take the same images, but this time from sketch universe, and we directly pass them to the classifier. As shown, the model fails, resulting in near random prediction. But this time, last time, we are passing the same images to diffusion denoiser before passing them to classifier. And as it can be seen, this restores performance back to near optimal accuracy, demonstrating the effectiveness of our data recovery approach. Additionally, we have evaluated denoising performance under different memory configuration. Here we define K as the packet to pixel ratio. And we vary this K from 1, the most relaxed setting, to 16, where there is almost no similarity between the sketch noise image and the ground truth clean image. The figure on the left shows the similarity between cropped image from sketch universe and their corresponding clean image before and after denoising. The figure on the right shows the box plot for AI performance for all the attack categories. As shown, even in the worst case, K equal to 16, the diffusion model is still able to recover meaningful signal and achieve strong performance for the majority of attack types. In terms of data plan, SketchVision is comparable to state-of-the-art sketch-based implementation in eBPF with a similar number of hash function and memory. For model performance, we measure per component latency. The denoiser takes 100 milliseconds, forecaster 11 seconds, and the CNN classifier 14 milliseconds, for a total of 140 milliseconds. The system currently supports up to 2,000 flows per second using off-the-shelf diffusion model. We leave diffusion, process acceleration, and model deployment as our future work, given the fact that slow and low attack relax latency requirement compared to a high-volume scenario. Let me conclude the talk. We discussed the limitation of existing detection framework for slow and low attack in CDN environment. We talk about scalability issue, evasion of coarse grain feature monitoring, and the challenge of working with partial flow observation. To address the problem, we have presented SketchVision, which enables scalable flow behavior monitoring through sketching mechanism. It trades computation for memory using diffusion-based denoising, and we are forecasting the mature state of the flow using a forecaster for early, both proactive detection of slow and low attack. For more information and result, please refer to our paper. You can find our source code in our GitHub repository. Thank you for your attention.